Continuing 12.5 global warming and Milankovitch cycles. Milankovitch cycles explain most of long-term changes, but not all. So what else is causing climate to change? Climate forcing is an imposed change of Earth's energy balance. There are positive effects, which increase temperature, and negative effects, which decrease temperature. A small climate forcing sustained over a long time can have a big effect. Here are some examples listed on the image. Increases in greenhouse gases, carbon dioxide, methane, chlorofluorocarbons, nitrous oxides, and ozone near the Earth's surface. These are all positive climate forcings in that they increase the atmospheric temperature. Same with black carbon, which is an aerosol byproduct from combustion. Interestingly, the sun, a non-anthropogenic climate forcing, has also been a little more active lately, heating us up a bit. Negative climate forcings include reflective aerosols, forced cloud changes, and land color change. These changes are actually cooling down the Earth a bit. Reflective aerosols include dust and other particulate byproducts that get into the atmosphere due to fuel burning and agriculture. Cloud forcing refers to the fact that we have more clouds now than before due to more aerosols and more water vapor in the air due to warmer temperatures. And clouds reflect a lot of sunlight and away from the Earth's surface. Land color change also deals with reflectivity, or albedo, not libido, albedo, of the land. So when all the positive and negative climate forcing numbers are added up, we get 1.6-ish watts per meter squared. Think of the Christmas lights mentioned earlier. Now you know what's powering the light. The big positive forcers are greenhouse gases. That should not be surprising. Here's a graph showing how the concentrations of three major anthropogenic greenhouse gases have changed recently. The x-axis is time, the past 2,000 years. The y-axes are concentrations in parts per million and parts per billion. Each gas has its own color, red for CO2, blue for CH4, and black for N2O. What do you see on the graph? Two important things to note. 1. Concentrations of these gases vary naturally. As seen before the Industrial Revolution. Second, the variance pre-Industrial Revolution is basically nothing compared to the exponential rise in these gases post-Industrial Revolution. And remember that these are positive climate forcers, meaning that they make the temperature go in a positive direction, as in up, warmer. So to further discuss why climate changes, here are a few terms for you. Climate sensitivity, the response of climate to changes after a new equilibrium has been established. And climate response time is the time required for the response of a forcing to occur. And keep in mind that climate may be inherently unstable. We will next discuss some reasons why. Ocean conveyor belt. Hear of that one before? It is the circulation of ocean water in oceans, as roughly depicted in the image. A change in the ocean conveyor belt can cause fast, i.e. decades, climate changes. Let's look at the image starting at the Atlantic Ocean. First, strong northward movement of near-surface waters are cooled when they arrive near Greenland. The water cools, becomes saltier as more water is evaporated off the warm surface water and therefore denser, and it sinks to the bottom. The current then flows southward around Africa. Huge amounts of warm water keep Europe warmer, 8.5 to 17 degrees Fahrenheit warmer than it would be otherwise. There is evidence that the cold reversal, called the Younger Dryas, that we looked at earlier, may have been caused by a disruption in the ocean conveyor belt in the northern Atlantic. The theory goes something like this. The Earth was just beginning to warm up from another ice age. Continents had massive stores of ice kilometers thick. As the cold, fresh glacial water melted, it often flooded into the ocean. In the North Atlantic, the water came from the melting Laurentide ice sheet and flooded out along the St. Lawrence Seaway. All that cold, fresh water diluted the dense salt water until it wasn't dense enough to sink. It also kept Europe cold and affected much of the northern hemisphere. Other fun implications with the ocean conveyor belt. So, the deep, cold water collects nutrients from the stuff on the surface that dies and falls down into the deeper water. So where we have an upwelling of deep, cold, nutrient-rich water, we also get fish, fish, fish. Fish are important for the fishing industries, of course. When El Nino disrupts things a bit, the fishing industry seems to be thrown into chaos. We are used to catching fish in certain areas, like Alaska, and that is in part due to the ocean conveyor belt bringing nutrients to these areas. Another takeaway from the ocean conveyor belt: it distributes heat. Europe is warmer than it has any right to be being so far north, as previously mentioned. Compare Europe latitudes with North American latitudes and you'll see what I mean. Compare Idaho and southern France. Also think about East Coast versus West Coast, warm water versus cold water, respectively. Climate change can also occur due to solar forcing. As aforementioned, there is a relationship between changes in solar energy and climate change. The medieval warm period, AD 1000 to 1300, corresponds to increased solar radiation. The Little Ice Age, mid 1400 to 1700, corresponds to decreased solar radiation. And currently, solar forcing partially explains climate change, but the effect is very small. The sun has a cycle of increased output every 11 years or so. Volcanic forcings also affect climate. Ash from eruptions becomes suspended in the atmosphere, reflects sunlight, having a cooling effect. Examples: Mount Tambora, 1815 eruption, contributed to cooling in North America and Europe. Mount Pinatubo in 1991 counterbalanced global warming during 1991 and 1992. And volcanic forcing is believed to have contributed to the cooling of the Little Ice Age. The image to the right shows a typhoon that generates dispersed ash cloud from Mount Pinatubo in the Philippines. Double whammy! So, other climate forcing that we've already talked about is anthropogenic forcing. Evidence of anthropogenic climate forcing includes recent warming of 0.2 degrees Celsius, 0.4 degrees Fahrenheit per decade. Cannot be explained by natural variability of the climate over recent geologic history. The industrial age forcing of 1.6 watts per meter squared is mostly due to emissions of carbon dioxide and other greenhouse gases. Climate models suggest that natural forcings cannot be responsible for a nearly 1 degree Celsius, 1.8 degrees Fahrenheit rise in global land temperature, and when natural and anthropogenic forcing are combined, the observed changes can be explained. Interestingly, reflection from aerosols are also causing a slight cooling called global dimming, which may offset up to 50% of expected warming from greenhouse gases. So we are also doing a bit of global cooling. But unfortunately, warming wins. Here's a graph depicting what I just told you. The x-axis is time. The y-axis axes are watts per meter squared for volcanic forcing at the top, solar forcing in the middle, and anthropogenic forcing at the bottom. The different color lines represent the results of different models. What do you observe? Here's some of what I see. The abrupt spikes in the volcanic forcing are volcanic eruptions that emitted a lot of ash. The solar forcing looks like there may be a larger, longer cycle on top of the 11-year cycle, and anthropogenic forcing totally wins by a whole heap on the warming side of things, though the sun is helping a bit. So, in summary, scientific uncertainties exist, but there is sufficient evidence to state: 1. There is discernible human influence on global climate. 2. Warming is now occurring. 3. Mean surface temperature of Earth will likely increase between 1.5 and 4.5 degrees Celsius, which is 2.6 to 7.8 degrees Fahrenheit during this century. And in case you didn't get it yet, human-induced global warming is from increased emissions of greenhouse gases. Increases in gases relate to an increase in mean global temperature of Earth, and there has been a strong correlation between the concentration of atmospheric CO2 and global temperatures as far back as we can see with paleoproxy data. And the trend continues today. (12.6) Potential effects of global climate change. Several potential effects of global climate change are very generally depicted on this world map. In fact, it is so general that it is mostly just useful for listing some of the major effects, which are coasts vulnerable to sea level rise, ice melting, increased precipitation and flooding, increased storm intensity, rising temperatures, more droughts, more wildfires. Note that the coasts most vulnerable to sea level rise are the coasts that have warmer water. Compare with the ocean conveyor belt. This is because just over half of sea level rise is due to thermal expansion. What are the climate changes that are likely to affect us in southwestern Idaho? What do you think? I bet you got it. Increased heat and more wildfires. We're also expected to get more and stronger wind. We are generally right near the border between different water predictions of less precipitation and more precipitation, so we look out and just be neutral on that. Only the future really knows. Back to global perspective. Glaciers and sea ice. We currently have a decrease in Arctic ice cap, ice sheets, and glaciers. This affects communities dependent on snowmelt for water supply and also affects sea level and sea salinity. And remember that sea salinity is a crucial part in maintaining the current ocean conveyor belt circulation pattern, which in turn is critical in distributing heat to various parts of the world, like Europe. The image is the collapsing Larsen B ice shelf in Antarctica, which was similar in area to Rhode Island. It took 35 days, starting January 31st, 2002, to totally collapse. The next image is of Arctic sea ice thickness, 100-year change. We are looking down on the North Pole. The norm for comparison is 1955 Arctic sea ice.